So in this video we are going to find out an expression for acceleration of any particle as seen from a rotating frame of reference. So as seen from a rotating frame of reference, the general acceleration term will obviously contain the centrifugal acceleration term or the centripetal acceleration term. Obviously, if you are talking about a rotating frame of reference, then we'll say the centrifugal acceleration term, and the other term will contain the Coriolis acceleration term, and we will have at least one other term which will refer to some other kind of fictitious acceleration. So to that end, let us first draw two sets of axes. The first refers to a coordinate system which is at rest with respect to the ground frame. So let's call this the x-axis, this the y-axis, and this is the z-axis, and our unit vectors along these axes are I cap, j cap, and k cap. Now let us imagine another frame of reference that is rotating with respect to the ground frame. Say this is our axis, the z-axis is the same for both of them, so this line represents both the z-axis and the z-primed axis. This is our x-primed axis, this is our y-primed axis, and along this line we have our I-primed cap, along this line we have our j-primed cap, and the k-primed cap is in the same direction with the same magnitude of unity, that is along the z-axis and having magnitude 1. Now let us draw a position vector. In one frame, let us call that position vector r, and in the other frame, that is in the rotating frame, let the position vector be called r primed. Because we are joining 2 points that are same in both the frames, the points will obviously not be different in the 2 frames. We can say that r vector equals to r primed vector. Obviously the description of these 2 vectors are different, but they are essentially the same vector because we have found that vector by joining two points which are common in both the frames of reference. So the position vector in the unprimed frame and the same position vector in the primed frame are obviously the same, although the orientation of these 2 vectors in the 2 different frames are different, and therefore the descriptions are different. That is, the x component, y component, z component in general will be different in the 2 frames of the same vector, but we are essentially talking about the same vector as seen from 2 different frames of reference. So the equality obviously holds. I think this point needs a little bit more clarification. So first of all, I actually should be writing r vector of t equals to r primed vector of t. The position vector r or r primed represents the position of this point, and in 2 different frames the vectors r and r primed, they look different, which means that they have different orientations in the 2 reference frames, and therefore they have different components along the x, y, and z axis as seen in the 2 different frames. But essentially we are representing the same vector as seen in the 2 different frames of reference, and this is true for all times t as the particle moves through space, with time being the parameter with respect to which the particle moves. So at a different time t, the position vector will be this, and it will have different representations in the 2 different frames of reference, but still we are representing the very same vector from the two different frames of reference, and therefore this equation will be true for all times t as the particle moves through space. That is one point. That is the first point that I wanted to make. And so wherever you see r and r primed, think r of t and r primed of t, with both r and r primed being vectors. The essential idea here is that vectors exist independently of the frames of reference or the coordinate systems that are used to describe the vectors. So here, these position vectors at all times t, they exist independently of the reference frames that we are using to describe those vectors. Obviously, in different reference frames, the vectors will have different representations, that is different orientations and different components, but all those components when added up will give us the same position vectors that we are describing with respect to different reference frames. Now, does this mean that other vectors, say the velocity vector, remains the same as seen from different frames of reference? Obviously not. So, for example, if with respect to the primed frame of reference, the particle that is moving or whose position we are describing with respect to time has a velocity v primed at some instant of time, v primed of t, at some instant of time, does this mean that when seen from some other frame of reference, the particle will have the same velocity? No. That is because when seen from different frames of reference, the velocity as a vector will become different. So, if we have defined the velocity of the particle to be v primed of t as seen from the primed frame of reference, we have the vector. We have already defined the vector. Now, this vector at this certain instant of time may look like this, maybe minus 2i primed cap plus 7j primed cap minus 3k primed cap. When we describe this vector from some other frame of reference, we have to keep in mind that we are describing this very vector, and from some other frame of reference, maybe a double primed frame of reference, it may look like minus 8 I double primed cap plus 11 j double primed cap plus 17 k double primed cap. But in that case, we are describing that same vector as seen from a different frame of reference. However, from a different frame of reference, the velocity of this particle as a vector will be a completely different vector. For example, in this video, we shall see that the velocity vector of a particle as seen from the unprimed frame of reference will be given by v primed plus omega cross r. Now, v primed, after we have defined it to be the velocity of the particle as seen from the primed frame of reference, we are talking about a specific vector, a vector that we have already defined, and this vector at that particular instant of time is a vector that exists independently with respect to the frames of reference we are trying to describe it from. Omega is also a vector that exists independently from all the frames of reference that we may try to describe it from. Same goes with r. So when we do omega cross r, maybe r at this particular instant of time, it looks like this. So omega cross r will be a vector that will go into the plane of paper. Let us represent it by this. So this is our omega cross r. If I draw it separately, if I take away all the props, that is the coordinate systems or the reference frames, then v primed of t is a vector like so. Maybe omega cross r looks like this. Now, v vector is the sum of these two. So it's a completely different vector. This is our v vector. which is given by v prime vector plus omega vector cross r vector, it's a completely different vector which has a completely different magnitude from v prime, and it makes a specific angle as with respect to v prime of t. Obviously all these are also functions of time, not omega. If we assume omega to be constant, that is, if we assume that the rotating frame of reference rotates with a constant angular velocity. Of course, if that angular velocity is changing, then this is also a function of time. But that is not the point I'm trying to make. The point I'm trying to make is that when I see the position of the particle from a different frame of reference, I'm talking about the same position. So I'm talking about the same position vector. But when I try to find out the velocity of the particle as seen from a different frame of reference, I have a completely different formula for that, and therefore I get a completely different vector. If I try to describe this vector from a different frame of reference, then I will obviously come up with this very vector, although my description will be different. But the velocity of the particle as seen from a different frame of reference is a completely different vector. So I hope that takes care of that little confusion. And another thing that I wanted to say with respect to the r vector is that if the origin of my frame of reference is shifted with respect to the initial origin, with respect to the first frame of reference, then obviously I am describing two different sets of points, only one of which is common in the two reference frames. Therefore, the position vectors as seen from the two different reference frames will be different. Obviously, that is not the case here because the origins coincide. So, if the origin was shifted, I wouldn't have been able to write this equation. R vector would not have been equal to r prime vector. So, if you imagine that the primed reference frame is rotating in some other direction, then maybe the angular velocity omega will look like this. But even then, when I describe omega, because omega is a vector now that I have defined omega, because omega exists independently with respect to the frames of reference from which I am trying to describe omega, again, from different frames of reference, omega will look different. That is, it will have different components along the different axes and also a different orientation. However, from the different frames of reference, I will still be describing this very vector. So in all frames of reference, if I write that the description of omega in some frame of reference is just omega, and in a different frame of reference it's omega primed, obviously omega and omega primed will be equal because I'm describing that same vector. But if my original frame of reference was itself rotating, maybe its omega was in this direction, let's call this omega primed and let's call this omega, then in that case the angular velocity of the primed frame with respect to the unprimed frame would have been different. So in that case, the angular velocity of the primed frame would have been something like this, omega primed minus omega. In that case, we would have been describing a completely different vector. So the angular velocity as seen from the frame of reference of the primed frame would have been different from the angular velocity of the primed frame as seen from the unprimed frame. However, in that case, the unprimed frame will not remain an inertial frame. So I hope this takes care of any confusion you may have had. Now, in general, from the unprimed frame, we can say that r vector is xi cap plus yj cap plus zk cap if the coordinate of this point is x, y, z as seen from the unprimed frame, and in the primed frame or the rotating frame this becomes x primed I cap primed plus y primed j cap primed plus z primed k cap primed. So I can also say that because this equality holds, I can do the same operation on both sides of the same of this equation. So let me differentiate with respect to time. In general, we are assuming that this point is moving through space as a function of time. Therefore, we can represent x, y, and z, and we can also represent x prime, y prime, z prime as a function of time. Although these functions will be different functions, x, y, z as functions of time will in general be different from x prime, y prime, z prime as functions of time. So d dt of r has to be equals to dy dt of r prime. However, we have to specify with respect to which frame we are seeing the rate of change, or we are trying to find out the rate of change. In this case, let me say that the unprimed or the non-rotating frame, let me call it sigma, and we are differentiating this equation from the sigma frame. We could have also done the same from the sigma primed frame, that is from the rotating frame of reference, but for now we are differentiating it or differentiating this equation with respect to time as seen from the non-rotating frame of reference, which we are calling the sigma frame of reference. This would not have been necessary, this specification would not have been necessary had we been dealing with scalar quantities. For example, let us consider a vector, say A, which has components ax, ay, and az in whichever frame of reference. If we differentiate ax, say with respect to time, and we do that in the unprimed frame, the differentiation will be same had we done it in the primed frame, because ax itself is a scalar. Although it may be a function of time, it's a scalar function of time, and scalar quantities do not change if we change frames in Newtonian mechanics. So we are only having to do this because we are dealing with vectors, and that too vectors which are if they are constant in one frame of reference, they are different in other frames of reference. For example, I prime, j prime, and k prime, they are constant vectors as seen from the primed frame of reference, whereas they are vectors that change with time as seen from the ground frame of reference. So in this equation, if we differentiate both sides, we will have to specify from which frame we are differentiating, which would not have been necessary had we been dealing with scalars. So the fundamental change that has taken place in going from the unprimed frame to the primed frame is that the unit vectors are changing with respect to time. So let me differentiate both sides of this equation. R vector being this, R prime vector being this, we are differentiating from the unprimed frame, and in the unprimed frame I, j, k are constants, whereas I prime, j prime, and k prime in general they are changing vectors. So differentiating the left hand side, I simply get I cap dx over dt plus j cap dy over dt plus k cap dz over dt. Differentiating the right hand side, we will get I primed cap dx primed over dt plus j primed cap dy primed over dt plus k cap primed dz primed over dt. However, we are differentiating with respect to the ground frame, and as seen from the ground frame, these unit vectors I prime, j prime, k prime, they are changing. In this example, I prime and j prime are certainly changing, but in general we can obviously think of a situation in which k prime will also change. So we get another term which is just x primed d I cap primed over dt. This is a vector differentiation, plus y primed d j cap primed over dt, plus z primed d k cap primed over dt. If you see closely, this is just the velocity vector as seen from the unprimed frame of reference. So we can simply call this v or v vector, which is simply dr over dt as seen from the unprimed frame of reference. The velocity vector as defined in the unprimed frame of reference is the rate of change of the position vector having been written in the unprimed frame of reference, and the differentiation also having been done in the unprimed frame of reference. In the same way, this is basically the velocity vector in the primed frame of reference, which is just dr primed over dt as done from the unprimed frame of reference, plus x primed d I cap primed over dt, plus y primed d j cap primed over dt, plus z primed d k cap primed over dt. Now we'll use another small equation. Suppose we consider a vector r which is constant in the unprimed frame of reference, that is in the rotating frame of reference. So if we differentiate that vector as seen from the unprimed frame of reference, that is as seen from the ground frame, that will just be omega cross r, because that vector which is constant in the primed frame of reference, that is in the rotating frame of reference, if that vector r is constant, it will rotate with an angular velocity omega as seen from the ground frame of reference. And because r and r primed are equal, I can as well simply put r primed dot equals to omega cross r primed. Now I cap, j cap and k cap, these are constant vectors as seen in the rotating frame of reference. So this formula holds for the I cap, j cap and k cap primed unit vectors. So this just becomes x primed omega cross I cap primed plus y primed omega cross j cap primed plus z primed omega cross k cap primed, which is just omega cross r primed. So we can say that dr over dt sigma equals to dr primed over dt sigma primed plus this term. But since r and r primed are equal, I can as well put r in place of r primed. So dr over dt as seen in sigma primed plus omega cross r. So this is a very important equation. Now we can now generalize this equation, and we can say that this equation is true for any vector. If you think carefully for a little bit, you will see that this equation has to be true for any vector, because this equation is true for a position vector. It will be true for displacement vectors, and any vector can be written as some multiple of a displacement vector. So we can say that this equation is true for any vector. Let's call that vector A. Now, let us, okay, the last equation can also be written in the following way: dr over dt, as done in the unprimed frame of reference, is just the velocity vector in the unprimed frame of reference or the ground frame of reference, and r over dt as done in the primed frame of reference, r being equal to r prime, this can be written as the velocity vector in the rotating frame of reference. So we have an equation v equals to v primed plus omega cross r. This also makes sense. If v prime is the velocity of a particle with respect to the rotating frame of reference, then the velocity vector with respect to the ground frame of reference will be exactly given by this formula. So, okay, by A here I did not actually mean acceleration, although we can do that too. By A here I meant any general vector. So in place of any vector A, let me substitute V. So if I do that, I get d over dt of V in the sigma frame of reference equals to dV over dt in the sigma primed frame of reference plus omega cross V. Now dV over dt in the sigma frame of reference is just the acceleration in the ground frame of reference. In place of V, let me substitute this V primed plus omega cross R, so I get dV primed over dt in sigma primed plus d over dt of omega cross R, which can be written as d omega over dt cross R plus omega cross dr over dt. Both these differentiations having been done in the sigma primed frame of reference, plus omega cross V. In place of V we can substitute this. If we substitute that, we will get omega cross V primed plus omega cross R. So this now becomes A equals to, this is obviously A primed plus d omega over dt cross R as seen in the sigma primed frame of reference plus omega cross dr over dt as seen in the sigma primed frame of reference plus omega cross V primed plus omega cross R. So we can write this as A vector equals to A primed vector plus d omega vector over dt, the differentiation being done in the sigma primed frame of reference, cross R, and this is just V primed, because in place of R we can write R primed. So the differentiation with respect to time of the position vector as seen in the rotating frame of reference and the differentiation being done in the rotating frame of reference can only mean the velocity vector in the rotating frame of reference. So omega cross v prime plus omega cross v prime is just 2 omega cross v prime plus omega cross r. So we finally arrive at our final expression for the relation between acceleration in a non-rotating frame of reference and acceleration in a rotating frame of reference. A prime is the acceleration in the rotating frame of reference, A is the acceleration in the non-rotating frame of reference, and we'll discuss more about this formula and solve maybe one problem in the next video.